For centuries, Isaac Newton's law of universal gravitation reigned supreme. It described the force that makes objects fall to the ground and keeps planets in orbit. But in the early 20th century, a young physicist named Albert Einstein revolutionized our understanding of gravity.
Einstein's theory of general relativity proposed a radical idea. Gravity is not a force acting at a distance, but rather a curvature of space-time itself. Imagine a bowling ball placed on a trampoline. The ball creates a dip, a curvature in the trampoline's surface. Similarly, massive objects like stars and planets warp the fabric of space-time around them. This curvature is what we perceive as gravity. Objects move towards massive objects, not because they're being pulled, but because they're following the curves in space-time.
Einstein's theory was a major departure from Newton's ideas and opened up a whole new way of thinking about the universe. It provided a more accurate description of gravity, especially in extreme environments like black holes and the early universe. To understand general relativity, we need to grasp the concept of space-time. Space-time is not just an empty stage where events unfold. Instead, it is a dynamic entity, a four-dimensional fabric woven from 3 dimensions of space and 1 dimension of time.
Imagine a vast sheet of rubber representing space-time. Objects with mass, like stars and planets, are like weights placed on this sheet. These weights cause the sheet to curve, creating indentations around them. This curvature of space-time is what we experience as gravity. Objects moving through space-time follow the curves created by massive objects, just like a marble rolling on the curved surface around the bowling ball on the trampoline. The deeper the curve, the stronger the gravitational pull.
Einstein's theory provided a beautiful and elegant explanation for how gravity works, uniting space and time into a single, interconnected entity. Einstein's field equations, a set of complex mathematical formulas, describe how matter and energy warp the fabric of space-time. These equations are like a cosmic recipe, revealing the ingredients and proportions needed to create gravity. The more massive an object, the more it warps space-time and the stronger its gravitational pull.
This is why a planet orbits a star. The star's immense mass creates a deep gravitational well in space-time, and the planet follows the curvature of this well. But it's not just mass that affects gravity. Energy too plays a role. Einstein's famous equation, E equals mc squared, tells us that mass and energy are interchangeable. Therefore, even massless particles like photons, which carry light energy, contribute to the curvature of space-time.
Einstein's insights revolutionized our understanding of gravity, demonstrating its intimate connection to the very fabric of the universe. Section 4. Wormholes, shortcuts through space and time.
One of the most intriguing predictions of general relativity is the existence of wormholes, hypothetical tunnels that connect 2 distant points in space-time.
Imagine folding a piece of paper in half and poking a hole through it. The hole represents a wormhole, a shortcut between 2 otherwise distant points on the paper.
In the context of space-time, a wormhole could potentially connect 2 different regions of the universe, or even different points in time.
A traveler entering one end of a wormhole could emerge at the other end, potentially billions of light-years away, in a fraction of the time it would take to travel conventionally.
However, wormholes are still theoretical constructs. While Einstein's equations allow for their existence, we have yet to observe them directly.
Moreover, their existence poses significant challenges and paradoxes that physicists are still grappling with. Section 5. The mystery of exotic matter. Keeping wormholes open.
One of the biggest challenges in understanding wormholes is their stability. According to general relativity, wormholes are inherently unstable and would collapse instantly upon formation.
To keep a wormhole open and traversable, we would need a special ingredient, exotic matter.
Exotic matter is a hypothetical type of matter with a negative mass-energy density. Unlike ordinary matter, which has positive mass-energy density and causes space-time to curve inward, exotic matter would have the opposite effect, causing space-time to curve outward.
This outward curvature, created by exotic matter, could potentially counteract the inward curvature of a wormhole, preventing its collapse and making it stable enough for travel.
However, the existence of exotic matter remains highly speculative. We have never observed it directly, and its properties challenge our current understanding of physics.